All right, top of the morning, everybody. So the last lecture didn't record right, so I wasn't able to upload it. But we kind of just introduced the notion of sheaves and pre-sheaves. And then we talked about the push forward sheaf. Um, we finished a proof from last time. But then yeah, so we defined formal sheaves. We defined the structure sheaf, ringed spaces, and yeah, that was it. So today we'll be talking about morphisms of pre-sheaves and morphisms of sheaves. So um, a morphism of sheaves, sorry, of pre-sheaves, of pre-sheaves of sets on X and phi. Or I guess it's on X and then phi is the morphism. Phi from one pre-sheaf F to another pre-sheaf. I'm trying to figure out, is there like a script G? That works. Script G um, is the data of maps phi view from the section of F on U to the section of G on U for all U behaving with respect to
Bless you.
thanks to the restriction that if you
Bless you.
thanks then the diagram f of v f of u f of v, no, that's not f, that's g.
Bless you. Jeez, you good?
Dude, I don't know what's been up recently. Let me blow my nose real fast, but then we'll finish the
Yeah.
diagram. Okay, so yeah, 5v sends these things over. Dude, I can't escape. 5u, and then respectively the restriction maps, res vu. And this commutes. And then morphisms of sheaves themselves are defined identically. One moment. All right. Morphisms of sheaves are defined identically. So the morphism from a sheaf F to a sheaf G are precisely the morphisms from F to G as pre-sheaves. So the only real data that we include at that point is kind of the gluing, but it doesn't change any of the underlying structure. And so, like, it just ends up being a full subcategory.
Yeah.
So, yeah, an example of a morphism of sheaves is the map from the sheaf of smooth functions. Goodness, smooth functions, excuse me, on R to the sheaf of continuous functions. So this is a forgetful map because we forget that the functions are differentiable and remember only that they are continuous. So we may as well set some topological, or sorry, we may as well set some notation. Um, um, let set x, ab x, etc. denote the category of sheaves of sets abelian groups etc. on a topological space X. Um, and then let mod, wow, I can't write today, mod OX denote the category of OX modules on X. Denote category of OX modules on a ring space X. And then let sets X pre denote the category of pre-sheaves on X and etc. Right.
Mm.
Okay. So, um, as kind of a theorem with a bulk statement, morphisms of pre-sheaves induce morphisms of stalks. And so this is called the stockification functor, right? So basically, this is kind of an important notion. Stockification. So let phi from script f to script g be a pre-sheaf morphism on x, and let p in x. Then there exists an induced morphism phi at p from f at p to g at p. And so what this does hmm, hmm. He's a little vague with the setup here. Um, well, let's pull in. I think we defined a stock over here. Maybe it was the previous lecture. Yeah, it was the previous lecture. Um, yeah, I mean it's just the stock of terms at P. So within defining. So um, if we start with the localization of the sheaf F, no, of the pre-sheaf F, E, then I'm pretty sure that this is defined to be on like just the ring of regular functions at P. I think, right? So just to be clear, this is an exercise. I'm stating
Okay.
as a theorem, but it's an exercise, hence my ambiguity.
Okay.
Um, Um, hmm. Yeah, so I think that it does look like this. And I guess really it's that we have a similar thing going on. So if this is phi, then whatever phi has is that it should work in a similar way, I think. So I'm just curious, is a stock always a stock of terms of functions? Let me Google this. Is a stock of a sheaf always a local ring? Yeah. Okay. Yeah, because it's a locally ringed space. Yeah. Okay. Understood. So we do have this right. Um, but I guess really we also have another thing going on. So 5p. Well, okay, hold on. This is fine, but it's not the
Yeah.
diagram that we need. Um, so like we're going from the localization at P of U localized at P to is it V? Yeah, it's V to V. And then we also have the restriction map. And I guess this is 5p. This is res VP UP res VP UP. Um, so this is what we need to satisfy with 5p. This seems pretty much self-defining. Um, I don't know. I feel like then that's okay. Like it just sends this the stalk at P of V to the stalk at V of P in both sheaves.
Yeah.
Okay. Um, Let me just Google the stockification functor to make sure that we're not. Yeah. Yeah, we've got it basically. Um, okay, so then as an exercise, okay, I don't even know. I don't think that that's a worthwhile exercise. Um, put this as a remark. Pi star f works for pi star um, from set x to set y. Um, and for other abelian categories. Yeah. Um, okay. So now we have a definition, which is that this is sheaf hom. Okay, so let f and g be two sheaves of sets. On X, and then let hom f to g be the collection of data. Dude, there is something in my eye. F comma script g of u is equal to the morphisms of f restricted at u to f restricted at g, or to g restricted at u. There we go. The word, you know.
Yeah.
um, Recall that the restriction of a sheaf to a single subset is in fact a sheaf.
Yeah.
Um, um, Yeah, so this sheaf is called sheaf ham. Um, Strictly speaking, we should reserve ham for when we are in an additive category. So this should be possibly called sheaf more, but the terminology sheaf ham is too established to uproot. It will be clear from your construction that, like ham, sheaf ham is a contravariant functor in its first argument and a covariant functor in its second argument. What?
Could you repeat that?
Sheaf ham, like ham, is a contravariant functor in its first argument and a covariant functor in its second argument. Oh, because this is ah right. So okay, what that means is in covariant terms, I just had a big thing click, not just for this. So they do script ham to get away with not calling it sheaf ham. I might call it sham. I'm gonna call it sham. Is that okay?
That sounds good.
Okay. In the book, if you're reading through it, it's script ham.
Okay.
We're gonna call it sham. Um, so as a covariant functor, this looks like going from f op to g at u, which is equal to more of f restricted to u op g restricted to u. So this is contravariant in the first slot, meaning that we just take the opposite of this thing in the category.
Mm-hmm.
So the error reversion. And then we take G to be the kind of covariant piece.
Yeah.
So like when we defined cohomology of sheaves, like we talked about how like you can induce cohomology from a chain complex, like 0 into dot 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 into AI minus 1, AI,
Yeah.
AI plus 1,
Right.
right? If this is a complex A dot, well, basically, if this is starting as a cochain,
Mm.
but then we can take the ham functor ham A dot to anything
Mm-hmm.
goes in terms of covariance as ham A dot op to
Mm-hmm.
wherever we're sending it. And then right derived functor of really gamma, which is a special case
Yeah.
of ham of A dot on a sheaf F is the ith cohomology group of A dot on a sheaf F. Right, so this was cohomology of sheaves, but basically the whole thing about covariance, really this should be A plus 1. Um, and then this should be A minus 1. Um, and then this is the statement, and then this is a chain. And then it turns into a cochain where it just switches the indices.
Oh.
So anyway, that was the thing that like I put together in my head of like, oh hey, that's where ham comes into this. Um, so So yeah, in terms of sheaf hum, this seems to be pretty well defined. I feel like I'm either missing something or this is very
Mm-hmm.
simple as an exercise. Um, I don't know. Um, as a remark, so Sham uh, from F to G localized at P is not isomorphic to of F localized at P, G localized at P. Um, and then there is at least one map from one of these to the other in which direction. Um, so these are the set of morphisms from FP op to GP. These are the morphisms from F op to G around P. And so I'm trying to think of an example, but like it seems reasonable.
Mm-hmm.
Um, so maybe if we had like I'm gonna assume that it'll work for OX modules because the Freight embedding theorem in OX module. Um, so hmm. So in terms of OX modules, then we really have I guess no, it'll be actual modules. So Sham from A to B localized at P is morphisms from A op to B in OX mod. and then round P. But what does that even mean in the context of morphisms of modules? So it's a morphism of Sheaves, which gives an OX U. Okay, so then, all right, so var phi in Sham AB has phi from script f of u to script g of u for every u open in X. And then I'm going to go out on a limb and guess that the localization of var phi at P is defined by f u p g u p. And then whereas psi in actual FP GP has psi defined from f of u of p. No, it's the other way around. It's the other way around. And then this is where it's the localization of the sheaf to a stalk versus the localization of X to P. And then we just need to show that f of UP is not equal to FP of U. So y is f of UP not the same as FP of U. Well, the localization of U at P is just the local is like it's just P inverse times A.
Yeah.
F of UP is equal to, with an abusive notation, FP inverse U, which is which gets mapped. Well, yeah. Whereas the localization of FP at U is the localization of the sheaf to a stalk. So this is still sheaf of ox modules whereas this is a stock at P over U of I don't know if it's a function, so on. Just over UP, whereas this is a stock at P over U. And then by the stockification functor, this is over the local ring of P intersect U. And I'm sure there's a case where these are the same thing, but I'm pretty sure that this is the right construction to show this. Okay. As a remark, he says, we will use many variants of the definition of Sham. For example, if f and g are sheaves of abelian groups on X, then Sham of abelian groups on X from F to G is defined by taking Sham of abelian groups over X from F to G at U to be maps of abelian maps as sheaves of abelian groups from restrictions at U to restrictions at U. Similarly, if f and g are OX modules, we define Sham of OX modules from F to G in the analogous way, and it's just an OX module. Obnoxiously, the subscripts abelian X and mod OX are often dropped here, so be careful which category you are working in. We call Sham mod OX from F to OX the dual of the OX module F. So I guess this is important. So Sham mod OX F to OX is equal to the dual of the OX module F. I just want to make sure that I'm understanding what an OX module is. So, because hold on. So, OX is a structure sheaf, and then an OX module is a sheaf of abelian groups, otherwise known as modules. on X such that for every open set U and X, f of U is an OX module. For every inclusion, it's also an inclusion module. It's a module object in the category of sheaves over OX. This is the sheaf theoretic analog of a module over a ring. And so the OX localization that we've been talking about is a family of modules varying continuously over X. So this notation A and B isn't exactly right. I guess it really should be from F to G, where F and G are OX modules. And then above, when we're talking about the localization, it's a family of modules varying continuously over X. And then the stock is a module of the local ring. So the structure sheaf is the unit object in the category of OX modules. Hold on. So OX modules. So like F equal to OX is a unit object in OX mod as a category. We haven't talked about vector bundles, but OX direct sum n, which is defined by sending U an open set to OX of U to a bundle n, is a trivial vector bundle. And then something more for us is if E to X is a vector bundle, which I'll define in a minute because I haven't ever had the pleasure of using one. F of U is equal to the gamma of U is an OX module, and locally F restricted to U is isomorphic to OX over R. So it's trivial vector bundles. What is a vector bundle? What is a vector bundle? F. So a vector bundle of rank R over a topological space X is a space? That doesn't make sense. hold on. Is a space E such that for pi from E to X, for every X in X, the fiber E at X is defined by pi inverse of X, is an R-dimensional vector space over a field K. And then for every X in X, there exists U open in X containing such that there exists a homeomorphism phi from U to pi inverse of U to U cross K over R meeting with projections. And just kind of as an implication, basically pi inverse of U is isomorphic to U over K to the R locally. So like at each point in the topological space, a vector bundle looks like that base point and a vector space. But like globally, all of the like vector space things might be twisted together. So like a trivial vector bundle is one where the entire space like is globally the same vector space.
Okay.
Whereas we identify a vector bundle as an OX module,
Yeah.
sheaf over an open set that is the global section functor of U into the vector space. And then at any specific open set as a restriction map, it's just the trivial vector bundle. Um, that is a really neat construction. Yeah. So locally free OX modules of rank R correspond to vector bundles of rank R. The cotangent bundle that we talked about, like M mod M squared, is also a vector bundle, I guess. Anyway, so towards our examples of OX modules, like I'm happy with that. Um, yeah. Um, so back to examples of OX modules. So fourth example, what did I do? Yeah, fourth example is if Z is a closed subset of X, um, then the ideal generated by Z over U is the set of F in OX of U such that F restricted to Z is equal to 0. Um, and then I guess this is F is in OX as a regular function. Wait, or maybe not. Hold on. Whatever the sections of OX are, okay, so it is a regular function. It is also a section of OX over U with the restriction that F over U intersect Z is the zero section. And so is it a regular function? Yes, it's a regular function that vanishes on Z. Or rather, if we take this at a point, it is the germ of a function near X that vanishes at X on Z. So like for concrete example, if we let X be Rn and we let OX be the set of smooth functions on Rn and we let Z be the ideal such that X1 is 0, then IZ U is equal to the functions, the smooth functions over U such that F of 0, N. I guess, is there a way to... F of like 0, comma, dot, 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 not necessarily 0, is equal to 0. So, like an example element would be like um, f of x1 through xn in iz over u could be like um, x1 squared e to the x2, because it's infinitely differentiable, but it's also vanishing at 0. Does that make sense?
Yeah.
Squared e to the x2 is equal to 0, and e to the x2 is in C infinity. Yeah. For a more algebraic geometry example, concrete example 2. Is let x be a point in our space, then let z be equal to the singleton set x, iz of u is equal to f in ox over u, such that f of x is equal to 0. And then this is the maximal ideal of the stalk at x, because these are the functions that vanish at just x. So OX modules are module objects over structure sheaves, which are basically like over functions. And see, okay. I'm missing the whole piece on like what an OX module looks like, because surely it's not like a matrix. An OX module is a sheaf of abelian groups Okay, that makes a lot of sense. So it's a ring of sheaves. No, it's a module of what? Okay. It is a system of modules. An object, wait. An OX module is a system of modules over local rings that are glued compatibly across the topological space. Okay. So an OX module F is a system or sheaf of modules over local rings OX comma X glued compatibly across X. So it's a sheaf whose coefficients vary with the open set that we choose. So when OX is the structure sheaf, OX modules basically become like collections of functions over a subset. And then as we change the subset, it changes the value that we evaluate them at. And so we look for like vanishing of OX modules kind of thing, like what we did with this ideal example. Um, yeah. Um, so I would like to take a 5 minute break. And I
Okay.
would like to go here and make sure that we actually understand everything that we've written down. And then we can continue on to pre-sheaves of abelian groups. Yeah.
All right.
So be back by 8:50.
Okay.
Okay, I'm back. I don't know if you're there, Garrett.
Hey, Tim.
All right. So, yeah, so with this understanding of OX modules,
Bless you.
let's just go back and look through this stuff. So this all makes sense. Um, this makes sense specifically on OX modules because we've just been talking about the localization thing. Um, and then yeah, in terms of this not being equal, we actually did totally have it right.
Hmm.
Um, that if we're talking about OX modules, that like f of u localized at p is not the same thing as f localized at p at u, because the localization of an OX module is in some cases just like, well, actually, shit. Do I know what it is? Because I'm fumbling. It's a local ring. That's what it is. So okay. Yeah, so f of p inverse u is still a sheaf of OX modules just over u localized to p. And then the
Hmm.
stock, yeah, and so actually what I wrote here is entirely correct, surprisingly.
Yeah.
That's very surprising. Okay. Um, okay. So the next section um, is called pre-sheaves of abelian groups, and even pre-sheaf OX modules form an abelian category. So, theorem pre-sheaves of abelian groups and even pre-sheaves of OX modules form an abelian. I just need a 1 minute real quick.
Yep.
All right. Um. Okay, so his remark here is that we can make module-like constructions using pre-sheaves of abelian groups on a topological space X. Throughout this section, all pre-sheaves are abelian groups. For example, we can clearly add maps of pre-sheaves and get another map of pre-sheaves, and then we define maps of addition as just kind of like splitting across sums. In this way, pre-sheaves of abelian groups form an additive category, and then by definition 1.5.1, the morphisms between any two pre-sheaves of abelian groups forms an abelian group. There's a zero object and one can take finite products. For exactly the same reasons, sheaves of abelian groups also form an additive category. So, if if phi from sheaf F or from a pre-sheaf F to a pre-sheaf G is morphism of pre-sheaves, then the pre-sheaf kernel of phi is a phi at U. Sorry. Is the kernel of phi at U. Okay, I'm a little lost. Nope. So the prekernel of phi is a pre-sheaf. And so for a proof sketch that is going to help us understand this, let U be an inclusion of V. Define the restriction map by this diagram. So for it to be a pre-sheaf, what do we want? We want, and this is a definition I really should be able to just rattle off. We want sections to exist. Um, and we want, so the kernel of phi at U is the set of, I guess, X and U such that phi is 0. X is equal to 0. So we want to show that this is a pre-sheaf, that sections exist, restriction maps exist, and that restriction maps commute. And so if we were to add an inclusion to this W, Then we could double this over. Res U, it's W, and it just occurred to me that I didn't change any of these. And then res U to W, then what we really want is we want the object of curpry phi. We want these restriction maps. So these, okay, I guess let me start with, these are sections,
Mhm.
right? So these are sections. And then these are the restriction maps that we want. And then we want this to be true. We want to have a restriction map from V to W. And so in terms of just showing that the restriction map exists, well, phi is from F to G. We have a restriction map from F over V to F over U by the inclusion of U into V. Then the kernel is the set of things in U which go to 0 from phi. And so phi is from F to G. And so really it's not X in U, it's X in F of U. And that was a key distinction that I did not make. In the section over U in F, they go to 0 in G. And so then we can recover the restriction by diagram chasing, like so. So what we'll do is to show that the restriction maps exist. So to show that res curpry phi v to curpry phi u exists. Let X be in the section of F over V with phi of X equal to 0. Then X is in cur phi, or pre-cur phi V. And so then, let's see. So X, so 5X is equal to 0 in G of V, but then res V to U of 0 is equal to 0 in G over U. The 0 section so there exists x prime in f over u with 5x prime equal to 0 in g over u, x prime equals x if x is in u, which is a subset of v. Otherwise, x gets mapped to 0 by this first restriction map by res like so. So the restriction maps exist. And then to show that, and this, yeah, we're kind of taking for granted that the sections exist, right? Like, we probably shouldn't do that. But like, I mean, okay, no, it's not for granted because every map will have a kernel.
Yeah.
So that's fine. That's actually fine. And then, yeah, to get down to W, we just kind of diagram chase twice. So I'm just going to say that composition of res maps just works. So yeah, okay, it is a proof sketch. But yeah, diagram chasing, lots of fun. Okay. Define the pre-sheaf co-kernel similarly. It is essentially a dual argument. So definition. So the pre-co-kernel phi is equal to co-ker of phi. I guess it's over U. It's all restriction maps. It is all restriction maps. Over U, which is equal to the image of phi over U mod the kernel of phi over U. And yeah, the rest was history. Oh, or not. Exercise. The co-kernel deserves its name. What is the universal property of co-kernel? Is it just what I wrote? Hold on. Definition 1.5.4. 1.5.4. A co-kernel. Oh, I don't want to do that. Okay. I don't love the category theory that much. Okay. It's not too tedious to verify that pre-sheaves of abelian groups form an abelian category, and the reader is free to do so. The key idea is that all abelian categorical notions may be defined and verified open set by open set. We needn't worry about restriction maps, they come along for the ride. Hence, we can define terms such as sub-presheaf, image presheaf, and quotient presheaf. And they behave as you would expect. You construct kernels, quotients, cokernels, and images, open set by open set. Homological algebra, exact sequences, and so forth also works open set by open set. In particular, and it says easy exercise, and this is where we get to find out if Ravi Vakil has a twisted sense of humor. A topological space X with an open set and a map from a sheaf or from a presheaf to a presheaf on that open set gives a functor from presheaves of abelian groups on X to abelian groups. Then show that this functor is exact. Okay. Um, Remark if U is open in X, then pi from F to F restricted to U is a functor from ab X pre to ab. Pi is exact. Um, so I'm assuming that F is a presheaf on X. And so what we want to show is that pi of ob F is equal to ob F over U, and that, or I guess that it maps to, yeah. And then that pi of more F is equal to more F over U. And then we want to conclude that abelian presheaves go into abelian groups. How is that? Is is a sheaf over an open set an abelian group explicitly? I think it must be, right? Just let me Google this. Is a sheaf over an open set an abelian group? Or is pi the functor that, yes, it is an abelian group. Okay. Yeah. Okay. So just a sheaf itself is a pre-sheaf of abelian groups because we don't have the notion of gluing together like abelian groups in F. But then when we restrict it to just one of them, it's an abelian group. And basically everything that's not in U gets sent to the zero object, and every morphism that goes out of U gets sent to the zero object.
Okay.
And then to show it's exact, we want to take an exact sequence. AI minus 1, AI, AI plus 1. And we want to show that it maps down to pi of AI minus 1 to pi of. I guess we want to think of it in terms of short exact sequences. So we'll characterize it with short exact sequences because um, every long sequence can be factored into short exact sequences. And we'll replace this with ABC. Pi of B goes into pi of C. Um, so we want to show that if this is A dot, then pi of A dot the pi of A dot is exact, i.e., if this is F, this is G, this is, I'll call it F prime, but it's really pi of F. And G prime at the kernel of G prime is equal to the image of F prime if the kernel of G is equal to the image of F. Now I'm going to write this first bit off to proof by intimidation.
Okay.
And then this second bit we can do. So if the image of F is equal to the kernel of G, then we have two options. So since we defined these things basically by inclusion maps or zero, basically pi of A is equal to A. It's really a piecewise thing. A if A is an element of FU, 0 otherwise, and then similarly for morphisms, pi of F is equal to F if F is in FU, 0 otherwise. And so if the kernel of G is equal to the image of F, then we want to let X and B be X in ker G equal MF. Then what we want to show is that we can take pi, then pi of X is in pi of B. But then G of X is equal to 0. So let's see. 0 and C. Oh, I see. So then pi of 0 in pi of C has pi of X in kernel of G prime, since pi of X is equal to 0. So pi of X is in kernel of G prime. And then we want to show that that's in the image of F. And then we'll want to do it the other way around. So pi of X is in kernel of G prime is non-zero if X is in ob F over U. So X is not equal to 0 in image of F, and pi of X is in M F prime. Thus, ker G prime is contained in MG prime. And then it's a similar proof to go the other way, I think. So I'll bump to viewer. So what is left to show is that the image of G prime is contained in the kernel of G prime. Okay. So pretty good day today. We made it through actually a bit of material. We'll start up tomorrow with an if and only if proof about exact sequences of pre-sheaves.
Okay.
And then we'll talk about sheafification. We are more interested in geometric objects like sheaves, where things can be understood in terms of their local behavior thanks to identity and gluing axioms. We will soon see that sheaves of abelian groups also form an abelian category, but a complication will arise that will force the notion of sheafification on us. Sheafification will be the answer to many of our prayers. We just haven't yet realized what we should be praying for.
Huh.
Okay. Let me go ahead and stop the recording. Thank you so much for tuning in today. And yeah.